So as you can see, we can at least come up with a mathematical formula to describe a particle, a tachyon, that travels at faster than light speeds. And we can also show how we can relate clocks for faster than light observers to clocks that are at rest. So the question is, how are these two seemingly independent Lorentz factors related to each other? So here in this slide, you can see that on the left side we have the Lorentz factor that Einstein developed, and on the right we have a similar factor called the tachyon Lorentz factor. And basically the only difference is that the ratio of velocity to the speed of light have switched. Now you can easily relate one to the other by using what's called an imaginary number. Now, an imaginary number is just the square root of -1. And when you multiply that through, it changes the denominator so that it reverses itself, so that the 1 falls behind it and is subtracted off, whereas in the other one it's in front. Now, I should say, in most calculations you can replace the Lorentz gamma factor with the tachyon Lorentz gamma factor and get some interesting physics to come out of it. Now, an important measurement is to study how the energy changes of a particle as it moves faster and faster at larger and larger speeds. So we have on the left here Einstein's relativistic energy formula, and we have m naught times the square root of speed of light, and the m naught just simply represents the rest mass of the particle if it weren't moving. And as it increases speed, the relativistic energy increases, so its apparent mass increases the faster it goes. Now, the interesting thing is, if you apply this same factor only using the tachyon Lorentz factor, what you find is that a tachyon will actually lose energy the faster it goes. In fact, when the velocity is instantaneous, it has 0 energy. So it actually takes energy to slow a tachyon particle down. Now we can graph this, and what I did here was I turned it into a unitless form by just dividing both sides by its rest energy. And we can see here a plot which shows the ratio of relativistic energy to the rest energy over the velocity divided by the speed of light. Let's just call it the warp factor for you Trekkie fans out there. Now, I should say that when particles are traveling less than the speed of light, we call these bradyons. And then, of course, photons are particles that travel at the speed of light. And like I've stated, tachyons are particles that travel at faster than the speed of light. Now, I'll just play this animation here, and you can see that they both increase. So in one case, the tachyon particle has to gain energy to slow down or to reach the speed of light, and whereas the bradyon has to gain energy to reach the speed of light. And you can see that it goes to an infinite peak when it reaches when it approaches the speed of light or near that of a photon. So a neat mathematical trick is to figure out how we can smoothly transition the light barrier without having this infinite peak that we have to cross. And so we need a function that will smooth it out, that will allow us to easily transition from a sublight speed to a superluminal speed. And this can be done by replacing that imaginary number with what I call is a transition function, which is just dependent on the velocity. Now, a real convenient one is to use the hyperbolic transition function. And it's basically a step function that starts out at +1 and then smoothly transitions to a -1. And you see here we have the hyperbolic tangent function. The sigma I just simply call the temporal coefficient. It determines the width of the light barrier, or the transition rate across the light barrier. And then it has to be normalized by the hyperbolic tangent times the temporal coefficient there. Now this function has some really neat properties. For example, when the warp factor, I labeled it here as beta, that's equal to the ratio of velocity over the speed of light. When it's much less than 1, you get a value of 1, and you get back the Lorentz factor that Einstein came up with. When it's near or approximately the speed of light, we get this ratio of the sigma over the hyperbolic tangent, and it basically just is a smooth diagonal line that transitions from 1 to a -1. And these are really good approximations that you can use when making calculations. And then, of course, when the speed is much greater than 1, or much greater than the speed of light, we get a -1. And notice that if we were to take the square root of all this, we get back that imaginary number that I talked about earlier. So in this animation, we're going to apply this transition function, and we can see that we have smoothed out the transition crossing the light barrier. So what this means is that the rocket ship will speed up and then smoothly cross over the light barrier. Now, the interesting thing about this is that we can have a large value to transition the light barrier, but it's finite. It's not infinite. And in later calculations that I made, I showed that as the particle approaches the speed of light and gains more mass, it starts acting gravitationally to the space-time around it. So it could be that this coefficient plays into gravitational effects with space-time. And I'll do a video later on about that. I'm excited to announce the premiere of my new documentary film, Time is a Fluid That We Ride to the Stars. In it, I discuss how we will design and build a micro warp drive engine that will take humanity up to speeds faster than that of light. Be sure and hit that notification bell and subscribe button so you'll be alerted to when it's available. Until next time, see ya on my channel, Hyperdrive X.